we present the projected distribution loss for image enhancement. The goal of image enhancement is to correct image distortions such as noise, compression artifacts, limited resolution, or image blur. We introduce PDL, a projected distribution loss for training deep image restoration models by directly comparing feature distributions. Comparing feature distributions allows us to recover images with more realistic details while still having low pixel distortions compared to other approaches. Deep models can be trained to restore images by using thousands of low-resolution, high-resolution paired examples. Training is done by finding the deep model parameters that minimize some loss function. The loss function penalizes the mismatch between the network prediction and the high-resolution reference target. We can, for example, directly measure the discrepancy in the image pixel domain by computing the square pixel reconstruction error. Inverse problems, such as image restoration, do not generally have a unique solution. There's typically an infinite number of high-quality images that can lead to the same low-quality observation. This implies that when minimizing the loss function, the network learns to predict the average of all possible solutions. The predicted image won't necessarily look natural and typically be blurry due to the averaging of many possible candidates. Here, you can see an example for a super-resolution network trained with an L2 pixel loss. The predicted image lacks of details and looks blurry. Many recent works have studied how to define losses that better characterize perceptual differences. The perceptual loss, also known as content loss, propose to compare the target and generated images on a deep feature space. The deep features are extracted from intermediate representations from a deep model, such as a BGG network, pre-trained for image classification. The perceptual loss leads to superior results in terms of perceptual quality, but still suffers from the regression to the mean on the deep feature space. An alternative approach is to use an adversarial loss where the generated images are forced to be in the manifold given by the high-resolution training data. This is done by simultaneously training two networks, a generator or restoration network, and a discriminator or a critic that learns to distinguish between real or fake images. The adversarial loss produces high-quality, realistic results, but it's hard to control the hallucinated content since it's not a reference-based distance, but a distance to the full manifold. Additionally, training might be unstable due to required minimax alternative optimization. Our solution is to adopt a loss function that penalizes the distance between deep features distributions from the network predicted image and the reference one. The distribution of deep features encodes relevant high-frequency information, such as image sharpness or texture grain, while being invariant to small shifts, noise, and other small changes present in images. The distribution loss serves as a complement to a regular pixel loss. To compare the feature distributions, we relied on optimal transport theory, in particular to the Wasserstein distance that measures the amount of work needed to transform or to move one distribution into the other. The Wasserstein distance between multidimensional distributions doesn't have a closed form, and generally an iterative numerical scheme is needed. For the particular one-dimensional case, the Wasserstein distance can be easily computed as a mean absolute difference between the two cumulative distributions. Since in practice we don't have access to the cumulative distributions, we relied on the empirical distributions. In this case, it can be shown that computing the Wasserstein distance amounts to sort the one-dimensional features and then computing the mean absolute difference. To exploit the good properties of the one-dimensional case, we adopt the slice Wasserstein distance introduced by Raban and colleagues. The overall idea is to project the data into one-dimensional subspaces and then compare and average the one-dimensional distributions. Here you can see an empirical distribution of a deep feature extracted from a VGG network for the reference image, the noisy low-quality input, the image recovered using the perceptual loss, and the image recovered PDL, our distribution loss. The empirical distributions of PDL is the closest to the reference one. We train deep image restoration models by minimizing a combination of a pixel loss and our distribution loss. The distribution loss is an average of the 1D Wasserstein distances between the independent distribution of deep features extracted from a pre-trained VGG network. Please check our paper for more details. Next, we present some results. We evaluated the PDL loss in different image restoration tasks, such as denoising, motion deblurring, single image super resolution, and compression artifacts removal. Here, we show a comparison on image denoising of models trained with different losses. Our projected distribution loss leads to generated images that have more details than when directly minimizing the pixel loss or other approaches like the perceptual loss and the contextual loss. Here you can see a close-up of the lion hair. PDL preserves the hair texture much better than the other approaches. To analyze the performance of the PDL loss, we trained and compared many different models using different balances between the pixel and distribution loss terms. We found that the PDL loss produces a better range of good quality results when changing the loss balance parameters than the traditional perceptual loss. Here you can see a close-up of the best found configuration for PDL and the perceptual loss. PDL better preserves details than the perceptual loss. We evaluated the proposed loss by comparing classical reference metrics, such as PSNR and the Structural Similarity Index measure, and also more recent perceptual quality metrics such as LPIPS and the non-reference based ones, NIQE and the Fréchette inception distance between the generated and referenced image sets. As expected, directly minimizing the pixel error produces the best PSNR while poorly performing on the perceptual metrics. PDL produces the best results according to the perceptual quality metrics while having a competitive PSNR. We validated our findings by running a user study where human subjects are asked to choose between one of two images in terms of perceived image quality. Overall, PDL outperforms the other compared models, showing the largest difference with respect to the non-perceptual pixel loss and the closest difference with respect to the contextual loss. Here we present some results when training models for single image super resolution. The results are superior to the ones with other reference-based losses and competitive to adversarial loss, while producing a lower distortion on the pixel space. Here we show a close-up of the best performing models. Thanks for listening. For more information about the projected distribution loss and additional results, please check our paper.